Okay, so exam one Monday, we're going to be covering chapters one and two. So the first, I think it's like the first two or three modules that you guys have gone through so far. Okay. So, the first few chapters are, just the basic intro to what chemistry is. Um, we, talk about some like states of matter, some properties, and then we go into a little bit of some of the math that's going to help us out later on in this semester. Okay. So let's go ahead here and get started. So number one, this asks for you to select which of the following properties is an extensive property. So we have luster, color, flammability, mass, or melting point. So anybody, if you want, you can like unmute or just drop your answer choice in the chat. So I need to look at what is an extensive property. Good. It's going to be D, mass. Mass is an extensive property. So you need to be able to distinguish between extensive properties and intensive properties, right? So what is an extensive property? An extensive property is the property of something that depends on the sample size. So extensive properties, this depends on the sample size. Or in other words, it depends how much you have, right? So an extensive property, again, it's depending on how much you have. It's dependent on your sample size. An intensive property is the opposite. And this one I think is pretty easy to remember because in intensive property, it is independent on the sample size. So in other words, it doesn't matter how much you have. Okay, so mass is extensive, right? It makes that just kind of makes intuitive sense, right? If you have, I don't know, if I have, say, I'm holding like a little Apple pencil, right? If I have, I don't know, say one of these weighs like 2 grams. I have 10 of these, it's gonna weigh more, right? I have more sample size, more mass, right? Um, Something like color or luster is intensive, right? It doesn't matter how much you have, right? I'm wearing a black shirt right now. It doesn't matter if I have 50 of these black shirts or if I just have one little thread of this shirt, it's still going to be the same color, right? So it doesn't matter. Okay, so any questions on number one with extensive and intensive properties? Okay. Number two, this says to identify the chemical change or chemical property. So our options, we have the fusion of water molecules to make ice. This word fusion is just a fancy way of saying freezing. We have solubility of silver chloride, the formation of rust, which is iron oxide under your car, shaping solid copper into a wire, or the vaporization of a puddle on the ground. So what here is chemical? Good. It should be C, the formation of rust. Okay. So a chemical change, right? It's gonna change the identity of that, right? Of that substance. Chemical changes usually are not reversible. Okay. Um, okay. Number three, which of the following name and symbol do not match? So there are three answers to this one. So I'll give you a minute to look over it and make your decisions. And again, it has three correct answers. Good. Yeah, your answers here should be A, D, and E. So beryllium, the symbol for beryllium is Be. For D, the symbol for potassium is K. And for E, the symbol for gold is Au. Okay. All right. Number four, which of the following is not an alkaline earth metal? So we've got magnesium, strontium, rubidium, barium, and calcium. Good. You should have C, rubidium. All right. So does anybody know on the periodic table where do we find these alkaline earth metals? Good. It's going to be group two of the periodic table. So, where's my thing here? So this is a website I use all the time. It's called P Table, and it's like an interactive periodic table. It's pretty cool. So, um, we were looking for what is not an alkaline earth metal, right? So you need to know that group one, these metals, so lithium, sodium, potassium, these are the alkali metals. Group two, these are the alkaline earth metals. Okay, so just make sure you know that. Okay. And if I'm like going too fast, a question pops up, just feel free to stop me. Okay, number six. So we were talking about the alkali metals, alkaline earth metals. So true or false, hydrogen is an alkali metal. What do we think? Is that true or is that false? It's going to be false. Good. So this is kind of a trick question because hydrogen is right here with group one, right? It's right above lithium. But even though hydrogen is there with the metals, it's actually a nonmetal. So yeah, okay. So hydrogen is a nonmetal. That's something you should know. Okay. All right. Number six here says to choose the statement of inequality. They should say equality, maybe. I think I made a mistake there. And also, sorry, I just remembered I forgot to mention this. This practice exam was posted to the eTutor and Canvas page. If you downloaded it anytime before like 1:30 this afternoon, you might have to download it again because I accidentally uploaded the wrong version. So if yours looks a little bit different, that's why. So I want for number six, I want to choose the statement for the prefix and exponent definition that is incorrect. So for A, is 1 nanomole equal to 10 to the negative 9 moles? And we think yes or no? Yes. So you need to know nano is 10 to the negative 9. For B, 1 kilomole, is it equal to 10 to the positive 3 moles? This is correct. So kilo, that prefix, it means 1,000. So 10 to the 3, right? 10 times 10 times 10, that's 1,000. For C, 1 centimole, is it equal to 10 to the positive 2 moles? No. What should it be equal to for centimole? This should be 10 to the negative 2, not positive, right? So it should be negative 100. Okay. Next, 1 megamole is equal to the 10 to the 6, 10 to the positive 6 moles, so that's good. And then 1 micromole, this little U, it's a Greek letter called mu. This means micro. So micro is 10 to the negative 6, or in other words, it's negative a million. Okay. Um, so this just comes from, if you remember in the chapter, it was the chapter one lecture. There was a chart with the SI unit prefixes. You must know that entire chart. Okay. Um, yeah, so it'll come back up. I believe I have another problem where it comes up. But knowing these conversions is very helpful when it comes to doing unit conversions and dimensional analysis, which is what some stuff we'll go over in a little while. Okay. Anybody have any questions up to this point? The exam review, it's where you joined this this call in the Canvas page here. Um, where am I? It's under files here. So why don't I have files on here? It probably looks weird on the iPad, maybe on this app. Yeah, it's in the files, so under the exam review worksheets you can find that. And also I forgot I need to so hold on. We'll do number 7, but just before I forget, I have to take attendance, so I'm gonna just drop a link in the chat that you guys could please fill out for me. So just before we do, so number 7 says that gold has a density of 19.3 grams per cubic centimeter. If you have a 20-gram sample of gold, what is going to be the volume? So I'll give you a moment to work on that, and I'll also give you some time to fill out this form that's in the chat for the attendance, please. And just to get you set up for number 7, we know we have to use the density equation. All right, so I'll give you a few moments to do all that stuff, and then we'll reconvene in a moment. How's everyone doing so far, in terms of the attendance and this problem? Everybody good? All right, so I'll start to go over number 7 here. So, I have gold, right? And it has a known density of 19.3, and I have the mass of the gold, and I need to figure out what the volume is of my sample, right? So we have to use the density equation. So density is equal to the mass divided by the volume, right? And from here, we can just plug in and do a little bit of math to figure out our unknown variable, right? So I have density, which is 19.3, equal to the mass here, which is 20 grams, divided. Um, is anybody else here having trouble? Does anybody not see files on Canvas? Is everybody able to? You guys can find it? All right. Maybe if you I don't know who was that. Maria, if you want, just you could put your email in the chat and I can send it to you by email. Okay, so back to this problem, right? So we have our density, we have our mass on the numerator, and then on the denominator is the volume, which is our unknown variable. So we'll write that as x. Okay. So just using like our mathematical intuition, does anybody have an idea as to how you would solve for this unknown variable down here? So to solve for an unknown variable in a fraction, what we could do is we can just cross multiply, right? So this 19.3, I can just put it over 1, right? Because any number over 1 is just itself. And like the name implies, we're going to cross multiply. So we'll do 1 times 20, and we'll set that equal to the 19.3 times x. Okay, so we cross multiply, right? 1 times 20 is just going to be 20. Set that equal to 19.3 times x, which should be 19.3x. Does this maybe look a little more familiar how to solve from here? Right, we're solving for x, so we can divide both sides by 19.3. So that way this will cancel off and we have x isolated. So what should be the volume of this 20-gram sample of gold that we have? Good. So okay, so we see you have x is equal to 1.04. Um, are there any units that go along with that? So we have the volume, right? What would be the unit for volume here? So the unit of volume here, you get it from the density equation. So remember, density is mass over volume. So the unit of mass is the gram. The unit of volume is centimeter cubed. So our volume is 1.04 centimeters cubed. Okay, and so just units are very important. Um, I always I always tell my students that a a number in chemistry without a unit is meaningless. Okay. So great, we did our math, we have our unit, but if it's the actual exam day, how would you enter your answer? Would you put like the full 1.04? Anybody have any thoughts about that? So there's just a little small rule that we're breaking here, which is honestly my least favorite rule. So I'm sure you guys have heard in the lectures of the significant figures, right? Sig figs. I hate sig figs. I think they're pretty stupid, but unfortunately for you, like for you guys, since your exams are online on Alex, you have to follow the sig figs or else it's gonna mark your answer wrong. Okay. So does anybody know the convention for reporting your sig figs in your final answer? So when it comes to reporting your sig figs in the final response, you need to answer. So you need to give your answer. All right. So do we know what significant figures are before I go on like this rant? So I guess I'll take that as a yes, a no. I don't know, but sig figs essentially it's used for precision, right? Say like I don't know, say like I'm measuring my weight, right? And I say I'm 135 pounds, right? Um, this has three sig figs, right? But this is not like it's not really that precise, right? Because chances are my weight is not exactly 135.0, right? It's probably, I don't know, 135.57, right? So notice how when you introduce these extra digits, you're getting more precise, right? You're being more like exact. So how many sig figs do we have here? This response, this number here, this has five. That's a five. And one other thing I always tell my students, my handwriting is garbage. So if I write something you can't decipher, just tell me. Right. So notice like, this is more like pinpoint, more precise, right? Whereas the 135, that's, a little less like exact, right? So why I bring that up is because when we give answers, we have to adhere to the least amount of sig figs, right? So the density, 19.3, this has three sig figs. The mass, 20, this has two sig figs. So when we wrote our answer originally, we said 1.04 centimeters cubed. This has three sig figs, right? But we need to give our answer to two sig figs. So we would say our volume is equal to 1.0 centimeter cubed. So just drop that 4 to keep the least amount of significant figures. Okay, any questions about that? Just really do make sure you look out for that because I don't want you guys, doing it right and then getting points taken off just for sig figs. Okay, so let's do another one. Number 8 says liquid mercury has a density of 13.6 grams per milliliter at room temperature. How many grams excuse me, how many grams are contained in a beaker that has a volume of 55 milliliters? So I'll give you a moment to look through this one and start it, and then we'll go over it. Maria, sorry, I totally forgot. I'm gonna email you this practice exam right now. My bad. All right, how are we doing so far, number eight? Anybody? No idea. Okay, no worries. So, in a way, this is kind of like the opposite of the previous problem we did, right? Again, we're dealing with density. However, in this problem, I give you the volume, and you have to figure out the mass, right? So, density is 13.6 gram per milliliter. That's equal to the mass, which is X, right? We don't know that, divided by the volume of 55 milliliters, right? So we're solving for X up here in our numerator. So again, we can just cross multiply. So the 13.6, put it over 1, cross multiply. So you're going to multiply your denominator by that numerator. And same thing with the other side. So 1 times X is just X, right? So the mass is going to be equal to what? It's the density multiplied by the volume, right? So you do 13.6 times 55, right? 13.6 times 55. And what do you get for that? You get 748, right? Can we respond with 748 grams? Is this following our significant figures? So this number seven, excuse me, this number 748 has three significant figures, right? Let's check with, we have to reference the information that we were provided with and check how many sig figs are there, right? So density 13.6, this is three sig figs. Volume, this is two sig figs. So I need to write this in two sig figs rather than three. Okay, so does anybody have any idea as to how I could do that? There's a there's a useful tool that we can use that we use a lot in, in chemistry and the math that we do in chemistry. So this number 748, right? This is like how we see numbers every day, right? We call the way it's written like this, we call this standard notation. But I'm sure you guys have also heard of scientific notation, right? So what we can do is write this number in scientific notation to conserve those sig figs, right? So remember, this has three sig figs. I want two sig figs. So how can I convert a number into scientific notation? Um, I don't know if she did this in the lecture or if you've done this like in past. schooling, but it's really not too bad. What you need to do is identify in the number where your decimal point is, right? So 748, our decimal point is after the 8. Okay. To convert it to scientific notation, all you're going to do is see how many spaces the decimal point jumps to get in between that first and second digit, right? So I want my point to be here between the 7 and the 4. So let's count how many spots it takes to get there, right? So we have 1, 2, right? So it jumped 2 spots. So our number should be 7.4 times 10 to the positive 2. Okay. If your decimal point is towards the right, it means it's a big number, right? Whereas if you had a decimal point here, if I had 0.748, that's a small number, right? So when your decimal point is jumping from right to left, the decimal is always positive. The exponent is always positive. If you're going the other way, if your decimal is going from left to right, that indicates a small number. So the decimal, God, I keep saying that. The exponent would be negative. Okay. Now, there's one more annoying thing about the math here. It was 748, right? There's technically an 8 after this. So, Alex, it wants you to round up. So, you would actually just write this as 7.5 times 10 to the 2 grams. And that's what your answer would be. Okay, any questions on, I know that was kind of a lot. Any questions in terms of like the math, sig figs, doing scientific notation? And I know like I'm kind of throwing this information out with you. It's kind of weird this semester that I don't have like a normal um SI schedule, but if you guys want, I can, because like, if it were a normal semester, I would like teach all this, you know, information first and then we'd put it all together. But I can send out my SI worksheets if you guys want that for the chapters. Okay. Um, One more thing I want to add with the math here. So I always do my math by cross multiplying. Okay. If you don't like that, that's fine. There is another way you can do it in which you can make what I call like a density pyramid. So we know density is equal to mass divided by volume, right? If I make a triangle and represent that, so density is equal to the mass divided by the volume, right? It's mass over volume. If you cover up whichever one of these variables you need to solve for, the pyramid will tell you what mathematical operation you need to do, right? So, for example, here we're solving for the grams, right? So if I cover up mass, right, you can like cover that with your hand. What do you have left? You have density times volume, which is exactly what I did here, cross multiplying, right? I did the density times the volume, which was on the bottom. Okay. So you can use that triangle. Some students like that. Personally, it's not really my thing, but it works. Okay. I should erase that. So any questions any questions on number 8 here? Okay. So let's move on to number 9 here. So I promise the last density one. So a piece of plastic has a mass of 5 grams and a volume of 6.5 cubic centimeters. Solve for the density and determine whether the plastic would sink or float in water. And here I provide you the density of water, which is 1 gram per cubic centimeter. So the math on this one is very easy because it's just straight up plug and chug, right? We know density, bro. Sorry. So we know density is the mass divided by the volume, right? I give you the mass, I give you the volume, so we have to figure out density, right? So we're just dividing. So the density is 5 grams divided by 6.5 cubic centimeter. Do that in your calculator, and yeah, good. So you're gonna get an answer of 0.8 gram per cubic centimeter, and this is going to float in the water, right? Why does it float? The density is less than the density of water, right? So, yeah, that's it. If, something like a rock, which sinks, is more dense than water, right? So, if it's less dense than water, it'll float. If it's more dense, it'll sink. Okay. And again, good, we have only one sig fig here, right? Because the mass has one sig fig, so we have to keep that the same. Okay. Number 10, true or false, argon is a halogen. What do we think there? So this one for number 10, this is false. Argon is not a halogen. Do we know what argon is? So let's look at where argon is in the periodic table. Argon is over here, element number 18. So all of these elements here in group 18, we call these noble gases. So argon is a noble gas. The question was asking if argon was a halogen. You need to know that, and it actually says it here, group 17, so fluorine, chlorine, bromine, iodine, all these. Group 17 we call halogens. So argon is not a halogen, it is a noble gas. Okay, and we're gonna talk a lot more about that later on in the semester. Okay, so any questions? I think this is page 2 so far. Any questions here? All right. Number 11, this says, which of the following depicts a mixture of both an element and a compound? So I want to see which of these boxes has both an element and a compound. So it's box A, box B, box C, or box D. Any ideas here for number 11 yet? Or do we need some time? Yeah, good. It should be box C. So, and I was kind of a jerk on this one. I like the answer choices are all like mixed up. So the answer is B for box letter C. Right? So how do we know that has both an element and a compound? So what is an element? An element only consists of one type of atom, right? A compound is going to be two or more elements that are going to be bonded together in a fixed ratio. And I will describe what I mean by fixed ratio. Okay, so an element, again, it's going to consist of only one type of atom, right? So here we have blue ball and a white ball, right? So box C, it's just, the blue is supposed to represent some type of element, right? So here's an element, here's the atom, right? These are the atoms of the element. And compound is two or more elements that are fixed in a fixed ratio, right? So what I mean by a fixed ratio is that a compound, right? Some like we all know what water is, right? Even if you never took chemistry a day in your life, you probably know that water is H2O, right? What does this mean? It means we have two hydrogens bonded to one oxygen. That is a fixed ratio, right? Two hydrogens, one oxygen. If I change this ratio, this compound is no longer going to be water, right? So what if I take my H2O and I just put a 2 next to the O, right? Is that still water? No, right? We obviously, well, hopefully we drink tons of water every day, right? We can drink water and, be just fine, right? Like you have to drink water. But if I make it H2O2, right? This is definitely not water anymore. You do not want to be drinking this, right? This is hydrogen peroxide. And if you drink that, you're probably going to be in trouble, right? So this is what we mean by a fixed ratio. Okay. Another example is like glucose, right? What the sugar plants make, what your cells break down for energy. Glucose is C6H12O6, right? The numbers, the subscripts, these ratios will never change, right? Because if you change the number, you're changing the compound. All right. Okay. Everybody good so far? All right. So let's get into a little bit of math here. All right. So, so we're still on like the chapter one material. So now we're getting into dimensional analysis. Okay. So dimensional analysis is super important because like I was saying earlier, in chemistry, the units are just so important, right? So, it's really important that we are, how do I explain? So, with dimensional analysis, it allows you to be able to interconvert between different units, between different quantities, right? Which is something that's really important to be able to do. Um, so units are super important here in chemistry. So when we're doing problems like this, it is imperative that you're writing your units throughout each step of the process. All right, so I'm gonna read this one to you. I'll let it kind of simmer a little bit, and then we'll go over on how to do this. So number 12 says fentanyl is an opioid drug that is prescribed for sedation and analgesic effects. And analgesic, this just means pain reducing. So we say that a burn victim is prescribed fentanyl IV drip at the rate of 45 micrograms per hour. However, we have a problem here, and the drug comes from the pharmacy prepared as 5 milligrams per 250 milliliters. So I want to figure out how many milliliters per hour of this drug should I administer to the patient? Okay. So, um, this is right. This is what we're starting with, right? The doctor says, this is what you need, 45 micrograms per hour. However, this is how the drug is coming prepared. So we need to figure out how many milliliters per hour we have to administer to this patient. Okay, so I'll give you like a couple minutes just to start working on it. We'll go over it and I'll be back in just one moment. All right, how's everybody doing so far? So at least what do we think we should start with? So I would start with the 45 microgram per hour, right? So before you even like look at the number, just look at the units because the units are gonna, are gonna be how you solve your way out of this. So what do we ultimately need to do? We have to go from micrograms to milliliters, and we're going hours to hours, so that's not even a conversion, right? So you notice that there's a problem here, right? That looking at the numerator of this problem, right? We're starting with micrograms on the numerator. Our final answer is going to have milliliters on the numerator, right? So that's kind of odd because, right, microgram is a unit of mass, milliliter is a unit of volume, right? So like mass and volume are, different measurements, right? So we have to use this number here as our conversion factor to get to our desired units, right? So just watch how I go through this, right? So we're starting 45 micrograms per hour. Okay. Let me draw you like a little roadmap here. So essentially we're starting with microgram per hour. Okay. The microgram, right? What is another unit of mass that we have? It's the milligram here, right? So we're gonna have to go here from micrograms to grams to milligrams, and then from there we can go to milliliters. All right, so just watch how I do this. I want to go first from the micrograms into grams. Okay, so I'll set up my first conversion factor here. Okay, and before we deal with the numbers, what units are going to have to go on the numerator? What unit will go on the denominator if I want to go from the micrograms into the grams here? So for units to cancel each other out, they have to be on opposite sides of the fraction, right? So I want micrograms on the numerator, sorry, on the denominator, and then I want grams here on the numerator. So you'll see that micrograms cancel each other out. Okay, now we're going to use our exponential values that are from that chart that we're going to have to memorize, right? So once you see that chart and you memorize it, you're going to know that 1 microgram is equal to 10 to the negative 6 grams. Okay, so now I am at grams per hour. Okay, so I'm here. Now we need to go to the milligrams. So does anybody know how to convert from grams to milligrams? Good. It's going to be 10 to the 3, right? So you know that 1 milligram has negative 1,000 grams. So there, your grams cancel off. Okay, everybody following so far? Any questions up to this point? All right, so now where am I? If I were to stop doing my math, where are my units? I have milligram per hour, right? I want milliliters per hour, right? So here's the weird thing where we have milligram, right? But we need to convert that into milliliter. So here is where we're going to use our conversion factor that there's five, for this drug specifically, it comes as 5 milligrams per 250 milliliters. So remember, at the end, I want milliliters per hour. So that means I want the unit of milliliters on top and the unit of hours in the bottom. And we already have the unit of hours in the bottom. So that's a good thing, right? So let's deal with the milligram to milliliter conversion now, right? Remember, I want the milliliters on top, right? And in the problem, we have a conversion factor, right? We know that so let's write the units first. The drug is coming prepared as 5 milligrams for each 250 milliliters, right? And then you can check your units. The milligrams cancel. What do we have left? We have milliliter per hour, which is exactly what I needed to figure out. So I want to give you a moment to plug this into your calculator and see how many milliliters per hour we should administer to this patient. And just as like a reminder for how you do the math, any numbers that are on the numerator, you multiply. Any numbers on the denominator, you're going to divide. So essentially, you're going to do 45 times 10 to the negative 6 divided by 10 to the negative 3 times 250 divided by 5. And you should get 2 milliliters per hour. Right? I think when you do it, it's about like 2.25, but we know we have to use one significant figure because this number here only has one sig fig. Okay, any questions about that? Okay. All right, so let's move on to number 13 here. So this is another true or false problem. The SI unit of mass is the gram. What do we think there? So this one is false. The SI unit of mass is the kilogram. All right. So I kind of spoke about scientific notation a little bit earlier, but I'll give you some time to work on this one. So what is the value 576 with a million zeros expressed in scientific notation? All right, so if you have an answer, you should say letter E, right? So again, you just have to find where your decimal point is and then jump to see how many spaces it takes to get in between that first and second digit, right? Um, I think just by looking at this number, we would all agree that this is a ginormously huge number. So the exponent should be positive, right? So our exponent is here, sorry, our decimal point is here after that last zero, right? So we just jump to get between the 5 and the 7, right? So you jump your spaces and you count to 12. So 5.76 times 10 to the positive 12. Okay. Any questions with scientific notation there? All right, number 15, this says to convert 325 kilograms to nanograms. So just, kind of just consider what units we have, right? We're starting in kilograms and want to convert that to nanograms. So would you expect to get a really small number or a really big number? You'd expect to get like a huge number, right? Because nanogram is a very tiny unit of mass, whereas kilogram is a pretty big unit of mass, right? So we're starting with 325 kilograms, right? Just so let me just pull this up so you can kind of visualize the chart I was talking about. So here's the unit conversion chart I was talking about. Okay, so this for this chart, you must memorize the prefix and the exponent that goes along with it. Okay, so and what I highlighted in blue, like these are just like the most common ones that you're gonna see. So if you wanted to kind of like eliminate a few, sorry, I thought I was gonna sneeze. If you wanted to like eliminate a few, just so I don't know, make your studying easier. But the idea is that this gray box is the basic unit, right? So it's just 1, 10 to the 0. As you go up, right, these are really big units. Notice that the exponents are positive. So like deca, hecto, kilo, these are big units. Whereas when you're going below the gray box, you have negative exponents, right? Micro, nano, milli. These are all very small units. Okay, so in the problem that we're doing, we're starting in kilograms, right? We want to get that into nanograms. So we're going from a really big unit to a pretty small unit, right? Now, um, I think it's best practice to instead of you can do your conversion straight from kilo to nano, but you just have to be really good with like your exponents and moving your decimal point. I don't suggest you do that because you're going to be much more prone to making the mistake. So I always do it by getting back down. So going from your starting unit, which is kilo, going back down to the base unit, which would be gram, and then from there going to your final desired unit of nano. Okay, so that's what we're going to do here. So I'm going to go again. I'm going to go from kilograms to grams, then to nanograms. Okay, so we have 325 kilograms. We want to convert that into grams. You know that 1 kilogram has 10 to the 3 grams. So your kilograms cancel off. And now I want to go from grams into nanograms. So gram on the bottom, nanogram on the top. And you know that 1 nanogram has 10 to the negative 9 grams. So the grams cancel off, and you're just left here with nanograms. So you do your math, and your unit will work out in nanograms, right? So you do 325 times 1,000 divided by 10 to the negative 9. And when you do that, you should get 3.25 times 10 to the 14 nanograms. Okay, does that make some sense? And again, it makes sense that we get a really big number, right? Because we have a pretty large quantity, we're converting that into a smaller unit, right? You could think of this almost like you could think of it like money almost, right? So let's say you have just like a single dollar bill and you have 100 pennies, right? it's the same amount of money, right? 100 pennies is in $1, and obviously just like a dollar bill is $1, right? But right, this is the same amount, right? Same amount of mass, but think of it like with the analogy with like a dollar and 100 pennies. It's the same amount of stuff, right? But if I go to the bank and I exchange $1 for 100 pennies, it's the same, same magnitude, right? Same amount of money. However, when I convert it to pennies, which is a small unit, right? I'm gonna have a lot of pennies, right? I'm gonna have 100 pennies. Even though it's the same value, I'm gonna have more tangible things because I'm going to that, that smaller unit. Okay. So that's kind of another way you can think about that. All right. Um, let's look at number 16 here. So how many atoms are in 2 moles of iron? So what do we think for that one? So what is the super important special number that you have to associate when you see atoms and moles? So hopefully we remember Avogadro's number, right? So what is the significance of Avogadro's number? Does anyone, sorry, does anybody know what Avogadro's number is? So Avogadro's number is a really important number, and I always tell my students you're gonna know this number like it's your phone number. So Avogadro was, he was a chemist way back in the day, and he was able to figure out how many particles are in 1 mole of a substance. So a mole we use as, right, um just like in common language, right? We use a dozen, right? A dozen is 12, or if you have a pair of socks, it's 2 socks, right? So a mole is kind of like a standardized unit in that way, in which 1 mole has a certain amount of particles, and particles, whether they be atoms, ions, or molecules. So 1 mole of anything has Avogadro's number of particles. Avogadro's number is 6.022 times 10 to the 23 particles. And this number you absolutely must memorize. Okay, so if I have 1 mole of chemistry students, I have 6.022 times 10 to the 23 students, right? Um, right, to the power of positive 23, this is obviously a ginormous number. But right, if we're talking about atoms and ions and molecules, right, those are so tiny, right? So we have to use large numbers to represent that. So knowing that 1 mole has 6.022 times 10 to the 23 atoms, how many atoms would I have if I had 2 moles of iron? Any ideas here? What we could do to figure that out? Right, so if 6.022 times 10 to the 23 is in 1 mole, if I have 2 moles, I'm gonna just multiply this by 2, right? So there's 6.022 times 10 to the 23, say atoms in 1 mole, right? I would just put my 2 moles here. So 6.022 times 10 to the 23 multiplied by 2, you're going to get D. 1.204 times 10 to the 24. Okay, any questions here? And again, if I'm like going fast, just let me know if you're confused. You can just shout out. Okay. Um, for number 17 here, I want to determine the number of protons, neutrons, and electrons in the potassium cation. So remember that proton is denoted by the letter Z. Neutron, we just use the letter N. And electrons, we denote by E negative, right? Because electrons have a negative charge. So how many protons, neutrons, and electrons do we think are in the potassium cation? So is there any way on the periodic table that we can get some of this information? So does anybody know how we can find the protons? Letter Z. Okay, so just a little rundown. So there are 3 subatomic particles, right? Atoms are made up of, other little particles. So the 3 subatomic particles are protons, which are positively charged, neutrons, which are neutrally charged, so a charge of 0, and electrons, which have a minus charge, a negative charge. Okay, so let's start with the protons. The also, used as it's denoted by the letter Z. So this one is the easiest to find out, and you can get that directly from the periodic table. So you might remember that the atomic number of an element is just how many protons it has, right? So you look at potassium, it's number 19. So that means it has 19 protons. So protons are going to be 19. Next, let's figure out the electrons. So we have the potassium cation, right? And we know that potassium makes a +1 ion, right? So how many electrons would my potassium ion have if it's a +1 cation? Right? So remember that the protons are positive, electrons are negative, right? So if it was neutral, you would expect that the protons and electrons are equal, right? But we have a +1 charge. So the potassium lost 1 electron. So we have 18 electrons. Okay. Finally, here for the number of neutrons, there is nothing on the periodic table that tells us that. We have to do a little bit of math to figure that out, right? So we have In the periodic table, we have again the 19, which was the atomic number, the number of protons, and we also have the mass number, which is the 39. Okay. Um, so something that you should know is that protons and neutrons have a mass of 1 AMU, whereas electrons, the mass is so small, we say it's negligible. So, um, mass number, so that like 39 that you saw, mass number is equal to the protons plus neutrons. So if I have the mass number and I have the protons, I can just subtract to figure out the neutrons, right? So for the mass number of 39 minus the protons, which was 19, we're going to have 20 neutrons. Okay, good with that. All right, next one, number 18 says that a jet ski travels in the ocean and its speedometer reads a velocity of 42 kilometers per hour. Convert the speed into miles per hour. So, um, we can just do some dimensional analysis again here. We're going from 42 kilometers per hour, converting it into miles per hour. Okay, and here I give you the conversion factor that 1 mile has 1,609 meters. We're going to have to use that. So first, let's convert from kilometers into meters. We know that 1 kilometer has 1,000 meters. So the kilometers cancel, and now I can convert from the meters into the miles by using that conversion factor. So I want the meters to cancel. I want the miles on top. And I know that 1 mile has 1,609 meters. The meters cancel, and you are left here with miles per hour. And you plug that in, you're going to get 26 miles per hour. Okay. The next one here, this is the last dimensional analysis. So the fastest pitch recorded during the 2024 MLB season was at 105.5 miles an hour. And I want to know how many feet per second the ball is traveling at this velocity. So you're always going to start with what you're given. We have 105.5 miles per hour. I want to convert that into feet per second. So I want the miles to cancel and I want to solve for feet. Here we know that 1 mile has 5,280 feet. So your miles cancel off. Now you have feet per hour. But I want to end up with feet per second, right? So what do I have to do with this unit of hours? Convert it into seconds. So we know that 1 hour, right? 1 hour has 60 minutes. 60 minutes have 60 seconds. So 60 times 60 is 3,600 seconds in an hour. So hours cancel, you have feet per second. So you solve that, you'll get 154.7 feet per second. All right. Number 20, which atom would you most expect to make a 3 plus ion? So what do we think here? So for 20, the answer is going to be B, gallium. Okay, so you need to know the common ion charges that are formed by elements in the periodic table. Okay, so you need to know group one, the alkali metals make a +1 cation. Group two, these make a +2 ion. Then this middle block, which we call the transition metals, you skip over those because they can vary. Then group 13 here, these make a +3, so this is why gallium is the answer. Group 14 you don't have to know because it's either +4 or -4, so you don't have to worry about that. Then you move over to the nonmetals. Group 15, this group, the elements in this group will make a -3 ion. Group 16, these will make a -2, and group 17, these will make a -1. Okay, so just make sure you know that. So that's why gallium is the answer. Okay. 21. The surface of the sun is about 5,800 Kelvin. Convert this into Celsius. So how do we convert from Kelvin to Celsius? What's like that special number we have to use? So remember to convert from Celsius and Kelvin, or vice versa, we have to use the number 273. So going from Kelvin to Celsius, we're just going to subtract by 273.15. So you should get about 5,527 degrees Celsius. Right, and then if we were doing the other way, if we were going from Celsius to Kelvin, you would just add the 273. All right, for 22, what is always the same for atoms of the same element? What do we think here? Any idea? So is it the number of neutrons, number of protons, number of electrons, number of neutrons and protons, or is it the number of neutrons and electrons? So what is always going to be the same for atoms of the same element? So the answer is going to be B, the number of protons, right? Remember that the atomic number is just how many protons it has, right? So if you change the protons, you're changing the atomic number, you're changing the element. Okay. Um, the neutrons, we know that's not always the same, right? Because we know we have isotopes. We have elements of the same, we have atoms of the same element that have different masses. And electrons, we also know is not right because when you change the number of electrons, you get ions, right? Okay. So number 23, this says that iodine is 80% I-127, 17% I-126, and 3% I-128. What is the average atomic mass for iodine? So we have to use the equation to solve for average atomic mass, right? Um, so just what average atomic mass is, right? You see, and I just mentioned I just mentioned what's it called? I just mentioned isotopes, right? So if you look at the periodic table, right, notice that the mass numbers, right, they're all like these really weird decimals, right? Really, it's not like a nice whole number, right? The reason why that is because the way that the mass is calculated, it's we take the average atomic mass for all of the possible isotopes that exist. So in a way, we're essentially just taking like the weighted average for the different isotopes of the same element, right? So here I give you the percent abundances of iodine and the relative mass. So you have to use the formula to solve for average atomic mass, in which you take the percent abundance, divide by 100, multiply by the mass for each isotope. So we have three isotopes. We're going to have to do this three times, right? So now we have the 17% I-126. So the mass of that is 126. Plus we have 3%. So 3 over 100 times 128. Okay, so you do that math, you put in your calculator, and you will get 126.86 AMU. But notice this 3% here, this is only one sig fig, so we have to use one significant figure. So we would just convert this and we'd say it's 1 times 10 to the 2 AMU for iodine. All right. 24, how many moles are in 6.83 grams of Al2O3? So so here's we're doing a little bit of the some calculations with the mole, right? I have 6.83 grams of Al2O3. I want to convert that into moles, right? So my grams have to cancel, and I want moles. So does anybody know how to convert from grams to moles? What do we have to use? So to convert from grams to moles, you have to use the molar mass, which you'll just find from the periodic table, right? So we have Al2O3. You're going to look at the periodic table, see how much aluminum weighs, multiply it by 2. Then you look at oxygen, which is 16, do that times 3, you add them up. So the molar mass for Al2O3 is 102, right? Your grams cancel, and you're just left with moles. So 6.83 divided by 102, this is going to be equal to 7.00 times 10 to the negative 2 moles. Okay. Number 25 here, name the compound K2SO4. So what would you guys call this compound? So we probably know what K is, but what is SO4? So K is potassium, right? SO4 is a polyatomic ion that you need to know, which is the sulfate ion. So this is going to be potassium sulfate. Okay. For 26, I want you to write the formula for titanium 4 cyanide. So titanium 4, right? For the transition metals, we have to use those Roman numerals to indicate the charge. So that means titanium is 4 plus. And does anybody know what the charge for the cyanide ion is? So the cyanide ion is -1. Okay. To write the formula from the ion charges, we have to do what I call a drop and swap. So the number of the charge will drop and swap with titanium. The same thing here, drop and swap. So the 1 goes with titanium, the 4 goes with the cyanide. So the formula here for titanium 4 cyanide is going to be TiCN4. All right, 27, true or false? The acetate ion is CH3COO minus. This is true. Okay. You can also see it written out as CH3CO2 minus. All right, any questions here? Is everybody doing all right? All right, so 28 says to name the following compounds. So just as a reminder, when you're naming compounds, you have to first decide whether it's covalent or ionic, and then from there, you know that they each have their own rules, right? So for A, this is, I'm gonna kind of just go a little fast here because we're kind of running short on time, but this is sodium fluoride, right? Ionic. P4S3, this is a covalent compound, so we have to use those numerical prefixes, right? So P4S3 is tetraphosphorus trisulfide. ClIOH is lithium hydroxide. DNaHCO3, this is sodium bicarbonate. And this is also known as, this is baking soda, by the way. And then PbI2 is lead 2 iodide. All right, any questions here? Okay. So this is like another naming or writing the formula one. So ammonium and carbonate combine to form a compound. Determine the formula for this compound. So ammonium and carbonate are two polyatomic ions, which you should know. Okay, ammonium is NH4 plus, carbonate is CO3 2 minus. So you drop and swap those charges. The formula here is going to be two, so it's NH4 2, so two ammoniums and then one carbonate. Okay. Number 30 here, this says what mass of carbon is present in 23.5 grams of C2H4. So I'm starting with 23.5 grams C2H4. I need to figure out how much mass or how many grams of carbon are in this thing, in this compound overall, right? So to do that, we have to first convert into moles. So remember to convert from grams to moles, you have to divide by the molar mass. So for the molar mass, you would do 12 times 2 plus 4. So the molar mass for C2H4 is 28 grams per mole. Okay. So now that you have a mole, you're in the moles of C2H4. From here, we need to figure out how many grams of carbon are in this 1 mole of this molecule, right? So in 1 mole of ethane, C2H4, I want to know how many grams of carbon are in there, right? So this molecule has two carbons, right? If you look at the periodic table, the mass of carbon is 12. So 12 times 2 is 24. So we put that for the mass, and your moles cancel off, and you have just grams of carbon left. So in this sample of ethane, if you have 23.5 grams, there 20.1 of those grams is just carbon. Okay, so there's 20.1 grams of carbon and 23.5 grams of ethane. Okay, now number 31 says ethanol, which is C2H5OH, is an alcohol. What is the percent composition of carbon in this compound? So ethanol, this is the stuff like, and this is, the alcohol and the drinks that we have. So like beer, wine, all that good stuff. So I want to figure out the percent composition of carbon in ethanol. So does anybody remember from the lecture how to calculate percent composition? What the formula is for that? Okay, so remember that percent composition, it's the number of atoms times the mass divided by the formula weight of the entire compound times 100. Right, so we're looking at carbon here. We have two carbon atoms. Carbon's mass is 12 divided by the molar mass or the formula weight of this entire compound. So you do 12 times 2 plus 5 plus 16 plus 1. The formula weight for ethanol is 46. Multiply that by 100. and you'll see the percent composition is 52.17% carbon. Okay, so just make sure you do know that formula. Um, all right, now we're going to move into writing empirical and molecular formulas. Okay, so just a little rundown if you don't remember. Remember that an empirical formula is the simplest ratio of atoms in a compound, whereas the molecular formula is going to be the actual composition of that compound. Okay, so in other words, the empirical formula is just like a boiled down version of the molecular formula. Okay, the empirical formula is the simplest ratio of atoms, right? Simplest ratio is going to mean like the smallest numbers. Okay, so I have a compound and it says that it has 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen by mass. Determine both the empirical formula and molecular formula for the compound. So I'm going to give you a moment just to get started, see if you remember how to do this. I'm gonna kind of just catch my breath for a moment and then we'll wrap up. We'll wrap up here, okay? Okay. So just to remind you of the steps to writing an empirical formula. First, you must assume that you have a 100-gram sample, right? So by assuming that, we can convert our percentages of mass to grams. Next, you need to convert from grams to moles. After that, you're going to divide by the smallest number. You're going to divide all of them by the smallest number, and that'll give you your simplest ratio. So I already did step one here, right? We assume a 100-gram sample, so we write everything as grams rather than percentages. Okay. Next, we're going to convert everything into moles. Again, doing that by dividing by the molar mass. Okay. So we convert everything into moles, right? Now we have to divide by the smallest number, right? Obviously here, 2.17 is the smallest number. So everything will be divided here by 2.17. Okay. Once you divide all of those numbers, that is going to give you your simplest ratio of atoms. So it's going to give you your empirical formula. Okay, so 4.34 divided by 2.17 is going to be about 2. And so note do keep track what element we're doing this for, right? So this is going to be 2 for carbon, 13.13 over 2.17 is about 6 for hydrogen, and then 2.17 divided by itself is just going to be 1, and that's for oxygen. Okay, here we have our simplest ratio, so our empirical formula is C2H6O. Okay, so that's just the first part of the problem. Now we have to figure out the molecular formula. Okay, so to get the molecular formula, what you're going to do, and I'll write that off to the side here. You're going to take the molar mass, which is given, divide it by the empirical formula, molar mass, and whatever number you get from that, you're going to just multiply to all the terms of your empirical formula. Okay, so the molar mass is, do that here, so 138.204 divided by the molar mass of the empirical formula. So you would just add these up. When you do that, it's going to be 46. So 138 divided by 46 is 3. You're going to take this number 3 and multiply it out all the terms in the empirical formula to get the molecular formula. So your molecular formula is going to be C6H18O3. All right, moving right on to our final page here. I know I'm just a little over my time, but we're almost done. So the identity of a metal can be found by determining its density. A 29.51 gram sample of an unknown metal has dimensions of 1.5 centimeter by 2.5 centimeter by 1 centimeter. What's the identity of this metal? So we have to figure out the density for this, right? Remember, density is the mass divided by volume. We have mass, and using the dimensions, we can figure out the volume, right? We know that volume is equal to length times width times height, right? So we're going to just multiply these 3 dimensions for the volume, right? So for the volume, you're doing 1.5 times 1 times 2.5 Your volume will be 3.75 cubic centimeters. And now that we have the mass, we can just figure out density, right? So density is mass 29.51 grams divided by the volume 3.75 cubic centimeter. And when you do that, you're going to identify this metal to be iron. So your density is going to be 7.87. All right, number 34 here. What is the mass number of an atom of elemental argon that has 18 neutrons? So remember, mass number, this is the protons plus the neutrons, right? So I'm given the neutrons, and I can find the number of protons just from the atomic number on the periodic table. So argon is number 18. So we have 18 protons plus 18 neutrons. So the mass number is going to be 36 AMU. Okay, and then finally, number 35, calculate the mass of vanadium 5 oxide in a sample that is said to contain a trillion, which is 1 times 10 to the 12 molecules of vanadium oxide. So I'm going from the molecules, 1 times 10 to the 12 molecules, converting that into the mass. Okay. Now there is no direct way to calculate from molecules to mass. We have to do a pit stop at the unit of moles, right? And we can certainly relate the number of molecules to a mole by using Avogadro's number, right? So the molecules cancel. I'm in the moles, and I now can go from the moles to the grams by using the molar mass. Okay. So what is the molar mass for vanadium 5 oxide? You just have to go to the periodic table, right? We know vanadium 5 oxide is V2O5. So just look at the periodic table, add those numbers up. The molar mass is 181.88 grams. So your molecules cancel, the moles cancel, and we're just left with grams of the vanadium 5 oxide. So 1 times 10 to the 12 divided by Avogadro's number multiplied by 181.88. This is going to be equal to 3.02 times 10 to the negative 10 grams of V2O5. All right, so that's everything from chapters 1 and 2 that you need to know for Monday's exam. Anybody have any questions at all? Anything from today or in regards to your exam on Monday? All right, well, thank you guys for attending today. Have a good weekend, good luck studying, and I wish you all the best of luck on Monday's exam.